in this lesson, we're going to be talking about logarithmic functions. So we're going to start by graphing a couple of functions. So we're going to graph the function. We're going to identify the domain, the range, the x-intercept, and the asymptote. So we're going to use our graphing calculator to assist with this. So let's make ourselves a table of values. All right, so remember to get a log with a base, you're going to go alpha window and then choose number 5. So we have a base of 2 and then of x. I'm also going to go to my table setup menu, which is second window, and I'm going to make sure that my table is counting by halves. So I'm going to put a 0.5 there. And I'm going to have it go ahead and automatically fill in that table for me. It doesn't matter where the table start value is. So I'm going to go to my table, and I have my table next to my graph. If you have it count by just, ones, you're going to miss any of the points between 0 and 1. So I like to have at least 1 point between where my asymptote is and that next integer. So I always do halves. That way I can get a point that's somewhere in here. All right. So if you notice, once you get to 0, you have an error. That's because you have an asymptote at 0. So I'm going to start in my table with the point that's a half to the right of my asymptote. So I'm going to start with 0.5, -1, and then I'm just going to choose points to graph along this. This one has some nice neat points like 1, 0, 2, 1, 4, 2, 8, 3. So I'm going to fill in my table with those values. So I have 0.5, -1, 1, 0, 2, 1, 4, 2, 8, 3. And I'm just going to graph those points. So half over, 1 down, 1, 0, 2, 1, 4, 2, and 8, 3. Now remember, you have an asymptote right here at 0. So when you graph this, this needs to come and get really close to that, but it doesn't cross at all or touch that, okay? So when you draw this in, you can start just a little before that right there. All right. And just make sure you don't touch or cross your vertical asymptote there. So let's talk domain and range. So for the domain, this is going to get really, 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 really close to an x value of 0, but it's not ever actually going to get there. It's just going to get really, really close. So I'm going to say that the farthest left this goes is 0, but I don't ever actually get to 0. I get right up next to 0. So I'm going to put a parenthesis to signify that I get really close to 0, but I don't ever actually get there. And this will continue off to the left, so all of the positive numbers for x. All right, for my range, this is going to continue to go down and down and down. So we're going to go -infinity, and then this continues to go up and up and up. So -infinity to positive infinity, or all real numbers. All right. And then let's talk x-intercept. So for my x-intercept, I can see that I cross the x-axis at 1. And then we already decided that we had an asymptote at 0. Now that's an x value of 0, so the asymptote is at x equals 0. It's a vertical line. All right. Now, if you'll recall, when we graphed exponential things, all right, they had a shape that was more like this, all right, and they had horizontal asymptotes. The domain was always -infinity to positive infinity, and then your range had like a bottom or a top. Okay, that's because those are inverses of our logs. So if I do the inverse, okay, it didn't ask us to graph the inverse, but, I'm going to. So for the inverse, that just means our x and our y's are going to switch. So our y's are now our x's, and our x's are now our y's. All right, and if we graph those, we're going to go left 1, up a half, 0, 1, 1, 2, 2, 4, and 3, 8. If I draw that in, that is an exponential function. Now, instead of having a vertical asymptote, we have a horizontal asymptote at 0. It'd be y equals 0. Instead of having an x-intercept at 1, we have a y-intercept at 1. Instead of having a domain of 0 to infinity, we have a domain of negative infinity to positive infinity, and our range is now 0 to infinity. And remember, when you graph inverses, they create a mirror across the line y equals x. So if you look, if you have a point here, then equally distant on this side, you have a point over here, or here and here, here and here, here and here. Those are mirror images across that line. All right. And then your domain, range, x-intercept, and asymptotes, those would all flip-flop because your x and your y's have switched spots. All right. So now we're going to graph the natural log of x. So we're going to make ourselves a table. Go back to your y equals, clear that out. Remember, the natural log is to the left of 4. So we have natural log of x. Then I'm going to go to my table. I can see again, I do have that vertical asymptote at 0. So that means my first x value is going to be 0.5 because I want to get a point between these two so that I have this little section. So again, these are not going to be nice, neat points on this one, though, just like they were on the first one. We had some good points. So we're just going to pick some numbers to fill this in. All right, so I have 0.5, negative 0.7, 1, 0, 2.7, 3, 1.1, 4, 1.4, and 8, 2.1. So I'm just going to graph these points. I just picked those. You could have chosen other points to graph, but we have over a half, down a little over a half, 1, 0, over 2, up a little over a half, 3, practically 1, 4, 1.4, so almost a half, and then 8, 2.1. So again, you have an asymptote there. Make sure you don't touch or cross that. All right, so I can see that my domain is going to be the same as last time. I'm going to start at 0, and it includes all the positive numbers. For the range, again, negative infinity to positive infinity. For my x-intercept, I'm still crossing at 1. And then for my asymptote, it is still at x equals 0. Now, just to let you know, I mean, these can shift different directions. So if I would have had like natural log of x plus 1, and that plus 1 was on the inside with that x, this would shift to the left one. So now my asymptote would be at negative 1 instead of at 0. If I would have said x minus 1, then it would be at positive 1 instead of at 0. So that would shift your domain as well. So it would be at 1 comma infinity instead of 0 comma infinity. If you add that 1 outside the parentheses, then it's going to shift your graph up 1, or if you subtract, then down 1, and so on and so forth. All right, so we're going to find the inverse. Your first order of business is going to be to switch your x and y. So x is now where y is, and y is now where x is. And you are solving for y, but y is in the exponent, and so you need to get rid of this base of 10. So the only way to get rid of a base of 10 is if you have a log with a base of 10. Now remember, when we have a log with a base of 10, we don't write the 10 down there. We're just understanding that it's there. So this log with a base of 10 is going to cancel, leaving me with y plus 1 is equal to log x. Then all I have to do is subtract 1. Y is by itself now, so I'm going to take that f of x up here, do the inverse notation. F inverse of x is equal to log x minus 1. All right, so we're going to switch x and y. All right, now notice on number 3, you did not have a log in your equation to begin with. So you had to use a log to get rid of that exponential base. Since you have a log, you need to use an exponential base. All right, so if you have a log to begin with and you're doing the inverse, you're not going to log your log. All right, so I see that this log has a base of 7, so I'm going to use an exponential base of 7 and take 7 and raise it to the left side, and take 7 and raise it to the right side. So 7 to the log base 7 cancels. So now I have 7 to the x is equal to y plus 5. I subtract the 5. Y is now by itself, so I'm going to use my inverse notation for g of x, which is g inverse of x, is equal to 7 to the x minus 5. All right, number 6, we're going to switch x and y. Now, again, notice you don't have a log, but your y is in the exponent. So in order to get rid of that base, you need a log with the same base. So since the base is 3, I need a log with a base of 3. So log base 3 of x equals log base 3 of 3 to the y plus 2. The log base 3 of 3 cancels, and I have log base 3 of x is equal to y plus 2. Then I'm going to subtract the 2. Y is by itself, so I put my inverse function notation. F inverse of x equals log base 3 of x minus 2. So we switch our x and y. Notice again, I have a log. So that means that to get rid of the log, I need an exponential base. Now, this log is not isolated. That minus 2 is not inside. If it was, it would be in parentheses. So the minus 2 is not inside the log. I need my log with that variable that I'm trying to solve for to be isolated. So the first thing I need to do is add 2. So now I have x plus 2 is equal to log base 7 of y. Now that that log with the variable is isolated, I can use an exponential base of 7. So I have 7, and since this is all over here already, I need to raise it to the top here, all of it. And same thing with this right-hand side. We have 7 to the log base 7 of y. That cancels. Now y is by itself, so I can go ahead and use my inverse notation. G inverse of x equals 7 to the x plus 2. Now I do want to mention that let's say that you had the x plus 2, and over here you had 7 to the y, and you had to do a log. If you log this side with the base of 7, you would have to put this in parentheses because there's already 2 terms there, and if you're logging those 2 terms, you need parentheses. All right. All right, number 7, switch your x and y. All right, now my natural log is already isolated. I don't have anything outside of the log on this right-hand side. So I need to use an exponential base of e. So this would be e to the x equals e to the natural log of y plus 3. That e to the natural log with the base of e cancels. So I have e to the x equals y plus 3. Subtract 3. Now my y is alone, but I didn't have function notation to begin with, so I'm just going to use y inverse is equal to e to the x minus 3. So number 8, let's switch our x and y. All right, we should notice right off the bat, my log y is not isolated. I need to move this 13, so I'm going to subtract 13. Now I can get rid of that log, and since there's no number in the base, we know that number is 10. So I have to take 10 and raise it to the left side, and 10 and raise it to the right side. So my 10 log base 10 cancels. Y is now alone. I started with f of x, so we'll have f inverse of x equals 10 to the x minus 13. All right, number 9. Again, notice I don't have a log, which means I'm going to end up using a log so that I can solve. So I'm going to start by switching x and y. My base with that exponent that I'm trying to solve for there is isolated. So to get rid of e, I need to use the natural log. So I'll use natural log of x equals natural log of e to the y minus 4. Natural log of e cancels. So I have natural log of x equals y minus 4. I'm going to go ahead and add 4. Y is by itself. So I have y inverse equals natural log of x plus 4. Number 10, switch your x and y. That base with the exponent is isolated. Since that's a base of 0.3, I need to use a log with a base of 0.3 on both sides. The log with a base of 0.3 of 0.3 to the y cancels. Y is by itself, so we have y inverse equals log base 0.3 of x. All right, number 11, switch your x and y. Again, I don't have a log, which implies I'm going to be using a log since y is in the exponent. So I need a log with a base of 6. So log base 6 of x equals log base 6 of 6 to the y. The log base 6 of 6 cancels. Y is by itself. So we have f inverse of x is equal to log base 6 of x. All right, and number 12, again, we're doing the inverse, so we're going to switch x and y. My log is already isolated, so since that natural log has a base of e, we're going to take an exponential base of e and raise it to both sides. The e to the natural base, or e to the natural log with a base of e cancels. So we have e to the x is equal to y minus 5. We'll add 5. So y is by itself. We have y inverse is equal to e to the x plus 5.